Okay, so now Amir is going to present 3D printed structure glass components, which I think is not a continuity, but so the printing powers that is manufacturing of this research that is ongoing at TU Darmstadt.
Benny, can you nod if the slide is shared? Okay, thanks, Benny. Okay. Yeah. Hi, thanks for everyone being here, and thanks for the opportunity to present. Sorry for this short delay. I just added this slide of the FDM printer to my slides also to talk a bit about in a more extensive way. This is also why I just cut off the this discussion. But I hope we can continue it then afterwards a bit further. So my presentation today is on 3D printed structural glass components. And yeah, my name is Amir Chhadeh, but don't go by Philip because we have another Philip here, and the other Philip has more seniority, so I lost my first name. Okay, so since we just had we talked about a lot of other materials, I just wanted to talk about glass in the built environment and where the trends are going. So I think all of you, even if you're not in the field of glass, you know the epicubes, and you know that transparency, larger glass planes, and more unique glass planes are something people are striving for, and that they have a effect for your company and advertisement that you get some kind of just showing that I have the greatest building and you can see through everything. And this is those are our use cases in the first time, and we hope that at some point we can sell our stuff to those guys. So enough about that. Additive manufacturing of glass. So there have been other successful prints, for example, from the KIT, from Mr. Kotz. The left one, the pretzel, and on the right side is from the MIT, the diffuse glass deposition modeling. They had a kiln with melted glass and moved the table under the kiln, and the kiln is funnel, of course, sorry. I moved the table and got a vase-like structure, as you can see here. The other one is with a SLA process, also just a singular object. I showed before on my slides that we want to go into facades, and this is why we believe that we need to fuse molten glass to flat glass planes. We have envisioned applications. I will also talk about other applications later in the slides, and would be grateful for some of you with your work experience in architecture also may have an idea. We'll just go through it one by one. On the left side is the a problem we were facing for a long time in classic glass joining techniques, for example, are boreholes and clamping, or gluing with adhesive, or for example, TSSA. And we face a lot of issues there with polymers. The material models are very difficult to calculate, but there was also a lot of advancement. The other issues are aging effects, weakness against UV, or humidity. The other issues with boreholes, it's always difficult to drill a hole into a glass plane, and afterwards you have to heat strengthen it. And it's a difficult process. Could be comparable to just add glass. So on the left side, you always see the conventional method. On the right side, the AM glass envision method is a 3D printed connector to a substructure. Also, this one on the left side, Kerstin just showed a render for it. Other options could be to stiffen glass planes. For example, in conventional glass facades, you have a 3-layer glass laminate. But we could potentially reduce the amount of glass we need by stiffening a glass plate. So I don't think I have to explain buckling to you or bending, but if you have a stiffener expanding it less of a problem. Yeah, then we also have isolated glazing or vacuum isolated glazing. I'm sorry. There we also need on the edges, we need a strong connection. It has to be very stiff. This could also be done with additive manufacturing of glass. And those ceramic spaces in VIGs could potentially also be just dots printed down with their printer. Yeah, there's a lot more to this. And I think we have to explain a bit better how to join fused glass to a glass plate. Here. So I brought a table, a graph, and we in the built environment, we often look through soda lime glass. Usually I would show now out of the window and say it's soda lime, but they are covered. Yeah, so we have to keep in mind what are the points of glass. So we have strain point, annealing point, which then correlates. We show this here to a temperature, and then we have the softening point, the working point, and at the working point, glass had the viscosity, for example, from honey. So I think everybody knows the honey from a tube. And then squeeze out. This is the viscosity we're talking about. Yeah, so we need to get the glass into a temperature where we can, we're in the area of joining viscosity. Yeah, so in the next slide, I would show it on an example of the point of fused glass onto a glass plate. So on the left side, you have an image of glass plate, point of fused glass in yellow, and then on the right side section. And our approach is to heat the glass plate to the glass transition temperature, which is for soda lime around 550 degrees. This is also the temperature where cracks should start to heal. Just to refer to our discussion earlier. Then the point of fused glass, which comes from our nozzle or funnel, needs to be at the temperature of the working point, so the viscosity of 10 to the power of 4 decipascal seconds. Yeah. And then what we also need to have is good enough viscosity. So the viscosity in the joining area here this needs to have the viscosity of joining area. So in between 10 to the power of 6 and 10 to the power of 4 decipascal seconds. Our approach here is to use the torch Cassian just showed you to join the fused glass to the glass plate. Okay, now following up on the question from Uli a couple of minutes ago, I just put in the slide from Cassian, to be honest. So we want to have an enclosed printing chamber with chamotte stones. So you can envision it's like an oven. And inside this oven, we want to have a temperature. So we heat the glass plate to 550 degrees and also have heated glass in there at 1200 degrees or 1300 degrees and a glass torch and a gas torch. So we have basically an oven where we can anneal afterwards. So in the oven, the chamber temperature is then also around 500 to 600 degrees. And there we have a controlled cooling process. The other issue I also see here is that we cannot wait always 2 days to get the specimen out of the printer. So we basically just put another oven next to our 3D printer, take specimen out, put the printed specimen into our oven and then anneal it there. And then we have to face the other issue. If you want to put a glass plate for the next print, the heated plates needs to cool down so that don't get a thermal shock. We can also think about if we have an oven on the side to have a preheated glass plate in there and put it in. Yeah, I think this is a bit advanced to go to mass production thoughts right now, but we're also having this in mind that we don't waste too much energy in just printing one specimen a week, just to cover this thought. Okay, now I just have to go one slide back, because then the storytelling is a bit more consistent. Regarding our point of fused glass, we need to transfer load from this additive strip or point or line of glass to the glass plate. And this is what I was focusing on in a preliminary study with the bachelor student, and also beforehand a bit more. We tried to make our own handmade specimen. So we just used a glass plate, put a strip of glass on top of it, put it in the oven, heated it to different temperatures. The left one is 775 degrees Celsius, and the center one is 800 degrees, and on the right is 825 degrees Celsius. So you can see in a range of 50 degrees of 50 kelvins, the result is a totally different one. Yeah. Now, what's important for us at the image below, because we don't want to have a sharp corner, because if we have a sharp corner and then put load enough, you have a singularity here on the edge. I can also show it on the screen. So at this edge, so we try to make it as smooth as possible. But you can also see if you heat the whole plate to too much heat or to too high temperature, you lose the shape of your glass plate. This is also something we don't want, because we then lose transparency. And yeah, as we know and love the built environment, they don't like wobbly glass. So we need consistent glass planes in facades that people can see through and light goes through. And this specimen on the right side just couldn't be usable in the facades. Maybe it will be at some point, it will be a trend, but currently we are rather looking for a straight glass plate and putting a strip of glass on top of it. Okay, now we dive just for a couple of slides into a bit of mechanical experiment. So we want to figure out, do an optical examination of those specimens, and we use a setup with the camera, those specimens, and there's a light source from the bottom. So the specimen is in front of a dark background, and then we can see what shape our added fused glass strip has. For example, those strips, those kinds of sections we can then analyze. We also use then MATLAB or W.AMCA algorithm to get the boundaries, and I hope you can see those red circles. So we can then say, okay, this is the contact angle between our fused glass and the glass plate, and then we can use simple equations to calculate our stresses after a shear test or bending test. And also we can just take the BW boundaries line, put it into a CAD model, and have the CAD model and just put it into ANSYS or whichever FE program is your least favorite. Okay, and then we also want to know how much load we can transfer, and then we have a test setup. For this test setup, we also use the photoelasticity setup Cassian just showed and explained. And in the center, we have the mechanical test. And in the next image, you can just see that we then just push with the cantilever from the top down, and it sits here. And on the back, on the front side, it's Teflon to have low friction. So there's basically no friction, but there's some friction. I'm aware of that. And now here in this image, we can see the reduced photoelasticity, the difference in the maximum principal stresses, but you can also clearly see in those lines that there's a compression force going through the cantilever to the support here on the left side. So I'm not that good with the mouse. Okay, afterwards we get then images like this. We can see how it shears off those fused glass strip. I didn't want to show like 20 pictures of those, so we often have this round shape, or the glass plate breaks through in a pattern like this. This often happens. And I had a small discussion with Philip yesterday. It's mostly like because there's a tensile component building, this leads to breakage in the glass then, because glass always cracks under tensile loads, because glass is very compression dominant. Yeah, this is our testing. So now I want to dive into applications and show what we have done by now. And I don't know who got the orange book from Beam from last year, but we put out our our exhibit. Thanks. Our exhibit. It's called Flip Desk because it's quite small. It's 500 by 500 millimeters. It looks like a desk. It behaves like a desk, and we just used four cones, which are printed by the Laser Center Hannover, which we have a research cooperation with, and they use a slightly different approach in 3D printing of glass, but they stick to the same mindset to fuse glass to a glass plate. Here you can see how they print. They use a CO2 laser and also use mirrors and a fiber conveyor on this part. So they add quartz glass, fused silica glass fibers on the base plate, heat it up with the laser, CO2 laser, and then fuse those fibers layer by layer on top of each other. The diameter of this cone here, the bottom, is roughly 25 millimeters. The height is also 25 millimeters, just for you to know. So it fits easily in the palm of your hands. So since the Laser Center Hannover is run by physicists, they don't have the application of the built environment. They are more like on another scale. It's compared to us more like nano or micro, as we learned yesterday. But we also use those the silica cones to find an application, and this was the flip desk. And now I just want to briefly show the methodology on how we want to use additive manufactured glass in the built environment on the example of the flip desk. So first of all, we checked for residual stresses, which were quite a lot here in our glass cones, but due to an annealing process in heating the silica glass cone to 1,400 degrees, we managed to get rid of the residual stresses. Then we have the next issue. Those plates are 40 by 40 millimeters, the base plates they printed on, and we want to have it on a larger glass plane. So we used the technique of laminating glass. In the first step, we need 2 glass planes. Those are now solder line glass because it's the most convenient glass we can get. We cut off the edges on the corners. Where is the mouse? On the corners, put a small wood safety cone on top of it, because in lamination, you then have your base plate, the PVB interlayer, which is just a polymer which glues through the process of heating and compression. Then we have the cutout glass. You can just imagine it like the Swiss flag, like a plus sign. And then on the edge, and then on the corners, you have those small glass volcanoes, cones. So cones, not volcanoes, maybe volcanoes. I think it sounds better. And then our lamination machine uses a simple process step. You just put a sheet of latex on top of it. Then with a vacuum pump, you suck out all of the air in between the glass planes and the PVB layer, so you don't have bubbles. And then afterwards, you put it in a chamber. You heat it up, and in this chamber, it's a closed chamber. You also add pressure on top. And with this, the PVB then is glued to both, to all sides, so to the glass cone and to the other two glass planes. Just as a FYI, PVB needs a temperature of 140 degrees to melt and then glue glass to glass or glass to PVB to glass. And those 140 degrees don't hurt the glass at all. So it's you don't have any residual stresses problems afterwards here. We also then, in a step before, now I skipped the logic a bit, we did a quick CT scan of the cones. And here you can also see that the laser center Hannover doesn't have a heated base plate. So you can see that the glass expands here, and the middle it pushes a bit together because there's a heat difference in the glass. So you have a bit of a wobbly effect. But nonetheless, you can see that the resolution is quite good and quite precise. So we can work with this. And I took the opportunity to just use this CT scan, put it in FE analysis, and calculated the rough. I did a quick calculation on those cones, and as you can see, also on this height, there's a small deformation in the cone. Yeah, somewhere above the line, and you can see then in the stress analysis that there's also a stress concentration there, but most of the stresses will then be where our double mechanism is connected to the glass cone. The double mechanism is just basic TPU print we just used from the CT scan. We can just cut out our object we need, print it, and then put it in place. Then we use the metal bolt to connect it, just like a double mechanism, spread out, and then it's locked in place. Now this is a step where I have to say we want to build in glass vertically. We don't want to build desks for everybody. We want to build facades. Facades are most often vertically. They have, of course, there are horizontal glazing, but also vertical glazing. And then I just flipped my calculation and applied the force in a different direction. And I thought that the stresses, so this is now in German on this, but you can see that the highest number is now 80 megapascals. And before it was 50 megapascals by the same amount of force. So in tensile stresses, it is not okay for glass because we just know the material properties and failure criterions for float glass. For flat glass, we don't know it for additive manufactured glass. So we have to keep a high safety margin. And this is well beyond anything we can say it's secure. So we got back to the drawing board and looked for compression dominant applications. So we don't want to have it on the top left in the bearing situation. We want to have compression dominant situation. For example, looking at a staircase, so staircase consoles, we can print, put a glass plane on top. We don't have lifting forces. In some way we do have lifting forces, but most of the load is in compression here. So we looked at the Apple Store in San Francisco with those laminated metal inserts. We thought, okay, we can also do this with additive manufactured glass. And now this is the same image now shown here in the section. And the next image, you can see a quite cool render, also done by Robert, on how we could envision doing a staircase. And we are currently in the building phase with the latest in Hannover, and we will exhibit this at GlassTech in September. This is now render, but the real thing, you have to go to Düsseldorf. Maybe we also go to Beam with this. Just go to Düsseldorf. It's cooler. Also, both are cool. Yeah. There we also do FE analysis, just to say this. And but we don't have to think about this. Now, the part I wanted to talk about now is ideas in mind. Ideas in mind, we do have now light diffusers. So on a glass plate, you can add whatever you like. You can print on your company sign or whatever, and can redirect light to the inside. This is something you can also think about glass sandwich elements. if you think about the MIT base structures, if you connect it to one plate, the other glass plate just rests on top, you have different bending moments than having just a normal beam setup. This could also be cool. Then we could, of course, flip the flip desk to the right side and use it as column and try to introduce loads in a wider area. So if you have a larger area, you have less stresses. And I have to be honest, the last sketch rather came to mind yesterday evening. This is why I also put out my laptop in the bar. I thought about a lot of the brick constructions most of you guys are doing, that you can also do like a connector here. So you have some kind of brick wall, and in the end, you add half of a brick printed in glass to a glass plate, and then connect it to a wall. This is just from the top of my head from yesterday. We can also discuss this. I don't see this now being an outside wall in this state of an idea, but I can also see it in the interior just to make a wall somewhere and make split some rooms in two. And you can also maybe then, because they're also glass bricks, switch it up and have some have storyline from like glass to glass bricks to clay bricks, ceramic bricks. This just also the bricks don't have to look like bricks. They can look like stuff you're doing, but I didn't manage to render it or do it since yesterday. So yeah, this is my latest idea. Thanks for listening to my talk, and I have to say sorry that I extended the time so much. And yeah, I would be glad to hear ideas and challenges you see in additive manufacturing of glass. And this is it. Thanks. So we have to, the question is how we can control the resolution in additive manufactured glass. Now I have to ask directly back, because we are at the moment on the way with two techniques, with the laser printing, which isn't done by us. This is done by Laser Zentrum Hannover, but they also do their resolution based on the fiber diameter, feed it, and the energy the CO2 laser has. On the other part of the fused glass deposition modeling, on the part we are working on with the printer under construction, the resolution, so the layer height, width, and is then regulated through printing speed and also the nozzle diameter. Currently, we are aiming for a nozzle diameter of 5 to 8 millimeters, especially since you've seen that the viscosity of glass in that grade, so we need a larger nozzle diameter to let the glass flow out of the nozzle. But this is, I think we will face the same issues as you with your resolution in clay printing, because those notches in between each layer, this will be the failure criterion for additive manufactured glass components to break, because you always have stress concentrations at each intersection. This is, thanks. Dunya, please.
Technique that is there to avoid or prevent crashing for glass, because maybe the load is ones.
Yes. Dunya's question is if there's some kind of mortar or soft interlayer between bricks and glass, and so there's the option to build glass brick walls, there's the option to build normal brick walls, and there's soft interlayers, they are out there. I would just, to be honest, I thought about just using them, but you saw it very correctly. I didn't put any mortar or something in my render here.
The load for the properties of the glass, maybe the load, it's not the.
Yeah. Okay. Yeah. Yeah. But you're talking about having a soft contact between the brick or stone and the fused and the glass component and glass plate or glass half printed brick. And yeah, there are lots of techniques to avoid stress concentrations between to have a hard contact on glass. For example, currently I'm working on another project. There's sheet material. It's called Surlyn, which is very transparent. It's easy to form under a very low amount of heat. So basically, with a heat gun, you can just put it on top of the sheet material, heat it, and then it stays in the same shape, but it's still a dry connection. So you can use it for masonries. Thanks. But yeah, you can also just use silicon as a fixed glue.
I have a question for which we should go to slide 8.
Yeah.
And so here we observe this interface, right? But again, the left picture, so the interface added art and the original target. You can see that in that slice that you made, right?
Yeah.
Now, if we go to slide 13, and we look at the part of the group, we still in the interface complete. And the thing that's lying on top, that's the different.
Yes.
Its head, see the interface.
Yes.
That's extremely in the picture because seeing this interface visually, I would expect that the fracture toughness in this interface is much weaker than the fracture toughness of the bulk material. So I would expect any crack that forms tiny rectangular notches to travel in the interface. But that doesn't happen. Really intriguing, really fascinating. Is that only this specimen, or is it?
Okay. So Philip asked on slide 8. He looked at the section for envision section of fused glass to a glass plate. Now he referred to slide 13 on if this is a typical crack behavior of our specimen. So first of all, those specimens are handmade. So I would prefer not to see the line at the interface, but I think this is obvious. Yes, we often saw this, and I would believe that this comes through that the glass strip doesn't shear off clean because we had enough heat to bond it, but on the other part, then due to the rotational aspect of the test, I think just also favors to break through the glass plate there. Yeah, I think we also had a short talk at some point. What failure models we see here? So shear 1 or shear 2. It's also hard to say in my opinion. I would rather go for 2 to have this sliding off.
Whether shear the wall off from that.
I would push the wall off from my side here. So from the right side. And sorry for Zoom, I don't know which side you are seeing. So from the shorter side to the longer side, wait, other side around. So we push the glass plate on this side, but the force will go from Bruno towards me.
Yes,
on the level.
This is beautiful. We see a 45-degree angle where the crack starts. That transformation of a pure hearsay that notch into a pure tensile stress state. Then the crack travels in a mode 2 dominated shear field where cracks tend to be 70 degrees out of plane. That's the red thing that you see.
Yeah.
This is perfect continuum. So thank class for being the middle of the show.
Yeah. But it's actually it's good to see that it checks out with the theoretical part. Yeah. Page 8.
There are significant colors, especially at the last one. You see, they're still writing from before. There's the same thing as Kerstin said before, that we have this decrease of different stress values.
Those are not taken through a photoelasticity setup. Those are just taken in the with this setup. Also, this is not the right setup because this was taken earlier stage because the student produced this setup to take the pictures, and in the first approach it was a white background. So this is why we're having a white background here. There's a different specimen, and he also looked at if it's worth the effort to put the specimen on a grinding plate to have a clear section, but it turned out it didn't have an effect on the MATLAB code. So this is just like probably so on the left one, we also saw some of these specimens with a circular saw. This is just some fragment of this. Sorry, it's not residual stresses.
Just like a question, also regarding these in slide 9. How did you use this? You took the kind of column and you have two wires holding the light.
Yeah, those wires, they're insanely large in this picture, but just to see that's not floating, this is also very, very thin.
Light is not deformed because you are making everything so. Sorry, what? Okay. So, but all you did the samples are
in the same position. Okay. We have, so this is also not entirely true, but you're very, very thorough in this one. So we have a setup to have the same distance between the camera and the box you can see, and then having the objective, the lenses. It's lenses who only focus on a certain distance. Yeah, the focal length. Thanks. You are an expert there. So you always see if the section isn't the right focus, and then we also, which we're totally true, we need an aspect to have a measurement between real life and picture. And I don't have it on my slides, but basically we use stickers, and then we have a sticker with a circle on it. Put it on. It's not here. So sorry, Benny. Basically, just put a circle on the center. We do the diameter of the circle, and with this we could get measurement for the pixel and height and length. This was easy way for us to just use like pre-printed stickers and put it on them. This was just convenient, not like rocket science. Yeah.
Thank you. Time for the break for lunchtime. And thank you. Very good. Yeah, thank you for reference.
Yeah.